so I don't really know why. Oh, it's so loud. I realized today could be a pants optional day. I didn't go to school. I didn't realize that yesterday. I still decided to wear some, but maybe. But it could be pants optional. Yeah. Could be pajamas. I could never do that though. I wore my sickle shirt though. I wanted to feel like I was actually at school. Okay, so Abby had her hand up. Which one would you like to take a look at, Abby?
Could you go over 15? It's the one
Yeah.
with a switch.
All right, so give me a second. I'm pulling it up. Number 15. That's a good one. All right, so initially the switch in the figures in position, it's like position A with capacitor 2 and 3 are uncharged and 100 volts. And then the switch is flipped to position B. All right, I think this is right in our wheelhouse. So what will be the charge on capacitor 1 after the switch is flipped? So this is very much in line with the kind of questions we tend to see on the exam. The exam loves this kind of stuff. The only thing that the exam really won't do that's happening here is the exam is not going to give us an exclusive capacitor circuit like this, where this is just capacitors. That's very unlikely. If they do, it's going to be multiple choice, believe it or not. They just tend to feature RC circuits instead because it allows us to discuss more complicated, not complicated is wrong, but more useful circuits. RC circuits are great because they take time. The resistor in the circuit restricts the flow of charged particles, and therefore you can tune an RC circuit, which is what we'll spend a lot of time talking about, the tuning of those kinds of circuits. But for the time being, we'll focus on what they've given us, which is this. So this is A, B, 100 volts, and my two capacitors are a 20 microfarad and a 30 microfarad. All right. And right now, switch 1 is, switch is in the A side. And this is what, 15 microfarads for me. So is that the same for all of you, or they give you different voltages?
It's the same for me.
All right. So the first thing we need to figure out here is that when we flip the switch, currently our circuit really doesn't have any of this in it. Right? This is our circuit for the time being. And when we flip the switch, the way the circuit's going to change is we'll have this now closed and all of this is gone. All right, so we really have two different circuits. When a switch does get flipped though, all of the energy is going to come from capacitor 1. And that charge is what's going to be used to distribute charges on capacitor 2 and 3. So let's start right here. Oops. And figure out what's happening here. We have a single capacitor, C1, charged to 100 volts, and it's 15 microfarads. The only thing we could probably do from this point is figure out the voltage on that capacitor and the charge on that capacitor. We know the voltage on the capacitor is going to be 100 volts. So all that's left to do besides that is figure out the charge on that capacitor. So getting the charge on that capacitor, not too hard here, right? So Q is going to be C times V, which is going to be what? 1,500 microcoulombs. Not good for all of you? All right. So next we're going to take that 100 volts out of the system, know that our capacitor is charged to 1,500 microcoulombs, and figure out how that's going to play off on our capacitor system. So take that away and throw the switch here. All right. So our capacitor has, right before the switch is closed, 1,500 microcoulombs and 100 volts. The two capacitors that are over there are uncharged. So when I throw the switch, we have a finite amount of distributable charge. Right? This is the total charge in our system. These three capacitors are going to distribute this charge in some way, shape, or form. And we know that from the bottom plate to the top plate, we have 100 volts of potential difference. So as we talked about yesterday, when we throw the switch to side B, we're going to have to distribute the system in such a way that the voltages or the potential differences for all connected conductors are the same. So my assumption is that they're going to ask probably for the charge and potential on the different capacitors. I assume I'm going to scroll down and see if that's true. They're going to ask just about C1. Okay. So let's see. Move this around a little bit so that's not right there. So got some space to work. Now, yesterday when we talked about this particular problem, what was the one thing we talked about when it came to like the charges here and the potentials here? You know, Alex is asking, is this a series circuit or is this a parallel circuit? And what did we finally end up on with that? Alex, you're the one who asked the question.
I mean, didn't we say that's not how you look at it, and you can't look at it as series or parallel? They just all have the same voltage with a finite amount of charge.
I think that's what we have to do. We have to figure out then from there, how do we know that we have 100 volts of potential difference from this bottom plate to the top plate. Now, I don't know if you guys realize this. When we close that switch, we are immediately applying 100 volts of potential difference from here to here. Right? The capacitor has that 100 volts. So when we connect it, we are making this the low potential side, this the high potential, and it's got to be 100 volts across here. Because that's what we did when we flipped the switch. I don't know if it's going to stay like that because the charges are going to redistribute themselves. But we applied this 100 volts immediately to the system in this way. But it's not going to stay that way. We know that what we're really going to get is we're going to get a flow of charged particles that's going to eventually have to distribute this 1500 microcoulombs around the circuit somewhere. So I think we write this as Q2, this is Q3, and this is Q1. And the first thing we say is that Q1 plus Q2 plus Q3 is going to have to equal 1500 microcoulombs. I think that's where we start. That's a clear piece of information that has to be true. Now, at the same time, we know that V1, V2, and V3 also all have to have something in common. I mean, the simple part is to say that, you know, we know that V1 is going to have to be equal to Q1 over C1. V2 is going to have to equal Q2 over C2. And V3 is going to have to equal Q3 over C3. Oops. Right? Now, we could do some substitution, but I'm not sure this all helps. What else do we know?
Doesn't Q2 and Q3 have to be the same?
Why would you argue that they have to be the same?
Because they're connected in series, technically.
Aren't they all?
Yeah, that's true.
I mean, you guys would say that that has to be true for all of them, but I don't know if they have to be the same. They would be the same if they were connected in series to a potential difference that was being maintained, like by a battery or something like that. But that's not the case here. We do know that the potential of this line has to be the same. They have to be at the same potential. And the potential of this has to be at the same potential. And the potential of this has to be at the same potential. How can we use that information in this instance? There is something we can do here, but I'm not exactly sure if you guys see what it is that we can do. And that's why I'm trying to see if you guys have an idea of where to go. Because I mean, we've got this one piece of information, but I don't think the charges are going to distribute themselves equally across this circuit. They're all different capacitances. I think they're going to distribute themselves so that these potentials are maintained.
I'm a bit confused. Is C1 and C2, would that be parallel? Like series? No, parallel. Right?
I don't think we can treat this like a series and parallel circuit. Not the way we would like to. I mean, ultimately, go ahead.
Can you rewrite the Q1 over C1 equals V1 equation, like all of them, for it to be Q is equal to CV, and then you could plug it into the total charge equation, and because V's are the same, you could distribute out of V and divide by the total capacitance to get what each potential difference has to be.
So, well, I know what you're suggesting. So you're saying V1 C1 plus V2 C2 plus V3 C3 has to equal 1500 microcoulombs, right?
Yep.
And you're suggesting that all of these voltages are the same?
Yes.
Why do you think they're all going to be the same?
Because once we hit equilibrium is where the total 1500 microcoulombs is equally spread apart with all of them to have the equal potential, so no electric field is created to push the charges around. And it has to be when electric potential is constant.
All right. I don't know if that's going to be true. I think this is going to be true. I think V1 is going to equal V2 plus V3. I think that's going to be true. And I want to see if I can help you guys see why that's true. Look at the picture that we drew. The red line has to be at the same potential. We already know that it was at the low potential, right? And the top line was at the positive potential, the green one, correct? Because that's where the 100 volts began. Everybody following along with that idea? Because I can't go forward until you guys all accept that this was the original bottom plate that was considered the low potential of the battery. And this was the original top plate that was the high potential of the battery. Is everybody okay with that? The charges are going to move, but ultimately, there had to be an increase in potential to go from here to here. And based on the fact that that red line all has to be at the same potential, the increase in potential from here to here, and then the increase in potential from here to here has to be the same as the increase in potential from red directly to green. So there's an increase in potential going from red to yellow. You guys can see the colors, right? I'm not just speaking to the colorblind. So let me zoom in here. Oh, that was not great. So this red line is the low potential. And this green line has to be the high potential, because our original 100 volts was right here. When we closed this switch, this whole red line had to stay at the same potential, the low potential. We know that we're going to be going up a potential here. This is V1. But on the other side, This V3 is an increase in potential that goes only part way to the full potential. And V2 is going to take us the rest of the way. The green line all has to be at the same potential, and so does the red line. So it takes 2 hops in increases in potential to go from the red to the green when I go through capacitor 2 and 3, but only 1 to go from the red to the green when I go through capacitor 1. The charges are going to flow, but we know that the green area all has to be at the same potential. The yellow area has to be at the same potential, and the red area has to be at the same potential. That has to be true. So when we're done, I think V1 is going to equal V2 plus V3 in order to maintain the potentials. You okay with that? Because I have another way of explaining it if that's not working.
Mr. Sheldon,
Yeah.
so I did the problem with it being in like series and parallel and I got it right.
There is a way to do it in series and parallel to get it right. That's what I was going to
Okay.
ask. Would you guys prefer to see it that way?
Yes.
Yeah.
Sure.
So if you want to do it as a series to parallel, you have to establish which capacitor is the one that's going to be considered our battery relative to our equivalent resistance. So this whole thing about talking about potentials might not be the right way to go for the way in which we've been talking about it. So let's, hold on. I can't make it smaller again. I can't make it go back down. Please, 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 sir, help me. There. Sorry. There, yay. So I'm just going to draw some things real fast. Our first circuit, right? That was our first circuit. This became 100 volts. This capacitor doesn't know it's about to be connected to 2 capacitors. All it knows is that it's charged and it's going to be connected to an equivalent capacitance. That equivalent capacitance is going to be C total, which is 1 over C total equals 1 over 20 plus 1 over 30. I'm taking the 2 capacitors and treating them as a single capacitor because this has become our battery. It was charged when it was connected to the other 2 capacitors. So to answer Alex's question from yesterday, because capacitor 1 was charged, it becomes the battery relative to capacitor 2 and 3. So I can choose to make that an equivalent resistance for capacitor 2 and 3. I have to get common denominators over here, which a good common denominator here would be 60. And I'll get 3 plus 2, or my total capacitance is going to be 60 divided by 5, or 12 microfarads. Now, for the time being, we're going to treat this as our actual circuit. So let's get that away. Let's go back to now saying that this was 100 volts and it had a charge of 1500 microcoulombs and a capacitance of 15 microfarads. Now, we have a fixed amount of charge, 1500 microcoulombs, and it's going to have to establish itself between these 2 capacitors in such a way that there's no electric potential difference between them. So we won't have 100 volts anymore, but we will have charge 1 plus charge on the equivalent resistance. has to equal 1500 microcoulombs. And V1 will have to equal VT. Now, we're not going to leave it like this, obviously. We're going to say that V1 is going to be Q1 over C1, and VT is going to be QT over VCT. So you can substitute that in here and get Q1 over 15 microfarads equals QT over 12 microfarads. And it doesn't matter which one we substitute, but we're going to have to substitute in here to figure out the charge on one of the capacitors. They want the charge on capacitor 1 as one of our answers. So it seems to me like the best way to go would be to substitute out the QT to get Q1. So I'm going to have QT equals 12 over 15 Q1. Now again, this is just treating that system together because Q1 was the charged capacitor, and so it became the battery. Now that gives us, when we substitute, Q1 plus 12 over 15 Q1 equals 1500 microcoulombs. So 1 plus 12 15ths, 1500. And I don't know what this is going to equal. But you're almost dividing by 2, so I'm thinking somewhere around 700 or 800. I mean, 12 15ths I could write better because that's 4/5.
830.3 repeating.
833
Mhm.
microcoulombs. Now, I don't know if they need the individual ones, C1, C2, and C3, or what do we do now? I guess I could look at the problem. I'm busy looking at you guys.
Eventually, they just kind of ask for everything.
Eventually, they ask for everything. So, well, at this point, boy, this problem is getting messy. Let's go ahead and do one more thing. Let's plug back in and figure out what V1 is now. So if you could do that, that would take that would help me out. So you're going to put your 833 microcoulombs, divide by your 15 microfarads, and I'll tell you what V1 is.
$55.6.
Okay. So, can't believe Mr. Shelton assigned such a jerk problem. So this is 55.6 volts. This has to be 55.6 volts. That doesn't tell me the individual, but it does tell me that that all has to be 55.6 volts. This is 833 microcoulombs. And whatever's left over has got to be the Q over here. Whatever charge is left. But I know the total has to be 55.6. Now again, these get to be treated like they're in series because this was the original battery. So because of that, this Q and this Q will have to be the same. Because I get to treat them as if they're in series. So it's going to equal C2V2 has to be one of the Qs. The other Q has to be C3V3. And these two have to be equal. But V2 plus V3 has to equal 55.6. Because that has to be the potential from the top to the bottom. So we'll get 20 microfarads times V2 has to equal 30 microfarads times V3. And V2 plus V3 has to equal 55.6. So it doesn't matter which one of these we eliminate. We need to find all of them. So I'm probably going to just go ahead and, I don't know, get 20 microfarads equals, not why did I do that? V2 equals 3/2 V3. So 3/2 V3 plus V3 equals 55.6. Keep going? Or do you think you guys have it from here? I can keep going. What do you think, Alex? Abby?
That is fine.
Abby?
That's fine.
All right. Now the real question is, the value for Q here has to be the same on both of them. Does it equal 1,500 minus 833? The original charge was 1,500. The new charge, 833. Or is it this divided by 2? I mean, the charge has to be the same on both capacitors. And we know we had a finite amount of charge. And we're going this way to find all the voltages. But we could find one of the charges. Could we have just figured out how much charge was left over, divide it in half, and spread it on both capacitors? Would that have worked? I think it probably would have.
Mastering has it as both of them have the 1,500 minus the 833.
So the finite amount of charge just separated the charges in the middle here. So you don't divide by 2, but they have the same charge because they had to attract the charges in between the plates. If that makes any sense. Meaning it's not like charge can jump the gap. This like little section right here is isolated. So you can't add charges in there somehow. So all that happened was when it was neutral before, when this suddenly became positively charged and this suddenly became negatively charged, the charges in the middle ran from one plate to the next. Because remember, we treated it like one capacitor before, but it was really 2 capacitors. So anyways, I do want to point out that little piecewise description, this becomes the battery. when it was charged first and then connected to these. Yeah. Not a great question, but probably a terrible way of explaining it to the class, though. I think I did a pretty bad job. So I'll do better on my second question. Maybe.
Can you do number 8?
I don't know. Based on how bad I did this one, I don't know. I'm not feeling very hopeful. You should expect a better teacher. But I'm sorry, you're stuck with me. I'm going to blame it on the hurricane. Everybody else seems to be blaming it on the hurricane. A vacuum insulated parallel plate capacitor with a plate separation of D has a capacitance of C naught. What is the capacitance if an insulator with a dielectric constant kappa and thickness of D halves is slipped between the electrodes without changing the plate? Okay. This is a relatively common style of question. So as we look at this problem compared to others, I would encourage you to realize that they like to ask these kinds of questions now. It's fairly contemporary. The test has merged over the last couple of years, and I think they've kind of fallen out of favor with asking strict capacitor and RC questions, and have begun to favor these kinds of manipulation of a capacitor by using a dielectric. So let's start by understanding that the capacitor by itself, the way it is set up now, has plate A, meaning it has an area of the plates equal to A, and a separation between the plates of D. And we're told that that capacitance, the original capacitance of the system, epsilon naught A over D equals this, C naught. Questions? Okay, so this is our original capacitor, but then we're going to take and place a insulator in here. And the insulator is half the thickness of the separation distance between the plates. Now, it doesn't really matter where I place this in here, but I'm placing it in the middle. Now, that's not the easiest way to do the problem, but I'm placing it in the middle right now for a demonstrative purpose. This is now D over 4, and this is now D over 4, and this is D over 2. We could treat this as 3 separate capacitors in series. One with a vacuum between the plates here, one with a dielectric between the plates here, and another one with a capacitor with a vacuum between the plates here. But what I want you to note about this is it doesn't actually matter where the dielectric is placed. I could take the dielectric and place it right against one of the plates, and it would be electrically the same as if I just floated it in the middle. Because it doesn't matter where it is, I'm still going to have these 3 capacitors, or in this case, 2 capacitors in series. The gaps, the amount of air, the space for the electric field hasn't changed. The thing I want to emphasize here is that capacitance is really based on how the electric field is between the plates, the amount of electric field that's stored there. And that hasn't changed whether I place the dielectric here or in the middle or on the bottom plate. None of that has changed. I have the same amount of volume, that's a vacuum, and the same amount of volume, that's a dielectric. So I think it's going to be easier to treat this as 2 capacitors than 3. So I'm going to treat it as 2 capacitors, and I'll call this top one C1 and this bottom one C2. And for the sake of our work here, the total capacitance of our system is going to be the sum of these reciprocals. Now we're eventually going to be comparing it to this capacitance. They want a ratio, but the way I think to do this problem is by doing it this way and doing it in terms of epsilon and A and kappa. So that's how I'm going to do it. This might not be the best way, but I'm going to call C1 is going to have epsilon naught A over D halves. And I'm going to say that C2 is kappa epsilon naught A over D halves. Everybody okay with that? Well, not getting much feedback, but I'm going to say 1 over C1 is going to be D over 2 epsilon naught A, and 1 over C2 is going to be D over 2 kappa epsilon naught A. So now I need to add those together. So I have D over 2 epsilon naught A plus D over 2 kappa epsilon naught A, and that equals 1 over CT. Now, I hope you notice that there's a whole lot of this that is the same. So I'm just going to factor out D over 2 epsilon naught A. And I'm going to be left with 1 plus 1 over kappa. That equals 1 over CT. Y'all good so far? Because I need to invert this. So it'll be easier to invert this if I get common denominators in here, which is going to give me kappa plus 1 over kappa. You guys good with that too? So invert both sides. So invert both sides. It's like I'm talking into the wilderness. 2 epsilon naught A over D times kappa over kappa plus 1. Now, I hope you all see that this is just the original capacitance. So to C naught times kappa over kappa plus 1. That should be our answer. Now, maybe it's nicer to take that 2 and throw it in there. I don't know. That way, all of this is just, your adjustment to the capacitance. Interesting here. If kappa is an integer, then it looks to me like unless that integer is 1, which would just be epsilon naught, that this increases the total capacitance, because it looks like this term has to be greater than 1. And the only way kappa would be equal to 1 is if the dielectric was just a vacuum. So putting this in there increases the total capacitance. That's not really a surprise, but I wanted to make sure we kind of digested that. All right. I don't know who asked that question, but there you go. Anybody else? No more questions? Fantastic.
Hello.
I'm here.
Okay, so why are we looking at as 2 capacitors? That's the one thing I don't understand.
The plates are immaterial. When we talk about the plates as a place where we store charge, they really are immaterial in that they don't contribute the way we think they do to capacitance. What we're really looking at here is how the electric field, remember, we found capacitance by looking at integrating the electric field for the potential. So when we look in here, the electric field from one plate to the other goes through two different materials. Well, the dielectric helps make the electric field easier to establish in the region of space where the dielectric exists. So in order to break down how that changes the strength of the electric field between the plates, we have to analyze the areas separately. So the only way to do that is to find a way to break up the space in talking about the electric fields. So a way we do that is treating it as if there's a place in the middle where charges are accumulating. Now, I would love to explain it more deeply than that, but the truth is I don't really know. I know this works, I know this is how you're supposed to do it, and there's probably a good explanation somewhere. I just don't have it. Because I mean, the other argument here, and this is one that you'll need to be able to make, is if instead of the capacitor leaving a space like this, what if our dielectric was like that? Well, in this instance, we would take and break this up into two capacitors that are in parallel, which might be easier to understand when we think of it this way, because I have a clear area where the plates have a dielectric in between and a clear area where the plates have a vacuum. So it might be easier to think of this as, two capacitors, one with no dielectric and one with a dielectric. That might be easier, but it's still just one object where just the overlap on one side has a dielectric and the other overlap doesn't. But we still break them into parallel and study them that way.
Okay.
So I don't have a better explanation than that. Sorry. Abby?
For question number 7, there's a question where there's like a dielectric with like Teflon, like a capacitor with Teflon inside of it.
Yeah.
Are we supposed to know the dielectric of Teflon for this question? Because like I found a table in the book that had it, but
That's what they're expecting you to do. You don't have to memorize dielectrics, no.
so like they would normally just give it to us.
Yes.
Okay.
Yeah.
Just making sure there wasn't like another way that it was missing.
No.
That worked.
No. They expect you to go to the book, look up the table, and then look up the breakdown electric field. So what electric field does the material break down? So you had to look it up, and I think the table is in the chapter. But again, if you're not looking for the book, you probably have to go to the old internet. But I will say this to all of you: in any of these problems, if they ask for a specific material and a property of that material, it's in the chapter. There'll be a table in that chapter with that particular material in that table. The book will be always a full reference to any problem that there is. They would never expect you to go outside of the textbook for a reference to something like that. So you might just want to crack open the textbook and look in that chapter. There will be a table right there that I guarantee will have dielectrics in it, or coefficients of friction, or masses of planets, whatever's in your question that would be related to that.
Mr. Shelton?
Yeah.
So I know class ended like 5 minutes ago, but I just want to ask.
I had no idea that the class ended 5 minutes ago. So
Okay,
you're gonna have to make this quick.
Yeah. Number 11. I just want to know if like you're ever gonna put that on a test, or if it'll be on the AP exam, because it was just like out of the blue.
Number 11. Yes. It's been on the AP exam dozens of times.
Okay, thanks.
So if it feels out of the blue, sorry, But let's make sure we talk about it on Monday, okay?
Okay.
Because the other thing is there's going to be questions where you have to pull the plates apart or push the plates together. Those kinds of questions are all over the exam. And yes, the expectation is we'll be able to do that. So if you need me to, I can extend the mastering if you guys do not get a chance to upload your information to mastering, or if you don't have access to the problems, I'll make sure it gets extended so you can take a look at it. And we'll continue to talk about this on Monday. Okay, guys? Sorry, I didn't realize class had ended. I wish somebody had said something. I don't pay attention. So I'm a bad person. Abby, I'll see you in like a second. Bye, guys.